Welcome to the solutions to the Regents Physics Work, Power, and Energy problem set, problems number 8 through 16. Also built within this is lessons on kinetic energy, potential energy, the work energy theorem, and the conservation of mechanical energy. So take good notes when you need to here. All right, we start with number 8. A compact car and tractor trailer are both traveling at the same velocity. Which has more kinetic energy? Well, we start by going to the reference table to see how do we calculate kinetic energy. And the kinetic energy, of course, is the energy an object possesses by virtue of its motion. And when we go to the reference table to look that up, we see that kinetic energy is calculated by Ke equals 1/2 mv squared. So if we compare the compact car and the tractor trailer, both have the same velocity, but both have different mass. You can see that there's a directly proportional relationship between mass and kinetic energy in both equations. Therefore, the one with a greater mass, which would be the tractor trailer, has the greater kinetic energy. The compact car with a smaller mass has less kinetic energy. Number 9, Brian and Andrea have identical compact cars. Andrea drives on the highway with a greater speed than Brian does. Which car has more kinetic energy? By saying that the cars are identical indicates to us that they have the same mass. So if we set up an equation for Andrea and an equation for Brian, Ke equals 1/2 mv squared, we're told that Andrea drives with greater speed than Brian does. So by increasing the speed, not only is the speed increased, but it's also squared. So by whatever factor we increase the speed, that factor becomes squared. So what we have is a direct squared relationship between velocity and kinetic energy. So by increasing the velocity, Andrea's kinetic energy is much more increased than Brian's, who has less velocity, therefore has less kinetic energy. All right, number 10, two bodies of unequal mass have the same kinetic energy and are moving in the same direction. If the same resistive force is exerted on each body, how will the stopping distances of the bodies compare? To answer this question, we are going to apply the concept called the work energy theorem. On your reference table, you'll find this as W equals F times D equals delta ET. We've already talked about work, so let's talk about ET. E is the symbol for mechanical energy. Subscript T means total. So total mechanical energy. Mechanical energy is the sum of all the kinetic and potential energies in a system. Well, the work energy theorem says that the work done on an object is equal to that object's change in total mechanical energy. So what we do is we start with that statement, and then in the next statement we write the forms of mechanical energy being changed in the particular problem. While rereading it, we have two bodies on unequal mass have the same kinetic energy moving in the same direction. Same resistive forces exerted on each body. How will the stopping distances of the bodies compare? So here's how we do this. We ask ourselves, are the objects' velocities changing? The answer is yes. It's going from some velocity to rest. So that means the objects have a change in kinetic energy. Are the objects changing a height in a gravitational field? No. They're staying on the same level surface, so there's no change in gravitational potential. Is there a change? Are they attached to a spring that's stretching or compressing? The answer also is no. So the only change in mechanical energy in this problem is change in kinetic. How do we calculate a change in any quantity? All changes are final minus initial. So our change in kinetic energy expression, W equals KEF, final kinetic energy, minus KEI, initial kinetic energy. The equation for W is F times D. And so our equation boils down to F times D equals, well, our final kinetic is 0 because the objects stop as indicated in our problem. And we're told that they have the same initial kinetic energy. So, if they have the same initial kinetic energy, and they both experience the same resistive force, then the displacement that both bodies undergo also have to be equal. Number 11. Two identical bowling balls are raised from the same height, one on Earth and the other on Mars. Which has the larger gravitational potential energy increase? Well, here I have a blue bowling ball and a red for the bowling ball on the Earth, and I have a red bowling ball for the bowling ball on Mars. Both bowling balls are identical, meaning they have the same mass. Which has the larger gravitational potential energy increase if they both go to the same height? Gravitational potential energy, PEG, is calculated by mgh. This, once again, found on your reference table. So if both have identical mass, both attain the same height, the one with the greater gravitational potential energy then is going to be the one with the greater acceleration due to gravity on that planet. You can see here that there's a directly proportional relationship between gravitational potential energy and the acceleration due to gravity on the planet. Well, when we compare the Earth and we compare Mars, the acceleration due to gravity on the Earth is greater because Mars has a smaller mass. So, since the little g value on Earth is greater, the bowling ball would undergo a greater potential energy increase on the Earth than it would on Mars. Number 12. Tony has a mass of 45 kilograms and is moving with a speed of 10 meters per second. A. Find Tony's kinetic energy. B. Tony's speed changes to 5 meters per second. What is her new kinetic energy? And C. How much work was done to slow Tony down? Let's start with A. Find Tony's kinetic energy. Well, this would be Tony's initial kinetic energy. So it would be 1/2 mv squared. 1/2 45 kilograms, her mass, times her speed, 10 meters per second, and remembering to square it. Most common mistake in calculating kinetic energy is forgetting to square the velocity when we calculate. We go ahead and perform the calculation, and we should get to 3 digits, 2,250 joules. In B, her speed now changes to 5 meters per second. What's her new kinetic energy? We'll call that her final kinetic energy, which would be equal to, again, 1/2 mv squared, 1/2 45 kilograms, times her new speed of 5 meters per second, remembering to square it. When we multiply those three numbers, 0.5, 45, and 5 squared, to 3 digits, we get 563 joules. Lastly, how much work was done to slow Tony down? This again is a work energy calculation. W equals delta ET. What form of mechanical energy is changing in this problem? Is Tony's speed changing? Yes, so there's a change in kinetic. Is her height in a gravitational field changing? No. Is she attached to a spring whose length changes? No. So the only change in mechanical energy is change in kinetic. That would be calculated by KEF minus KEI, final kinetic minus initial kinetic. Her final kinetic was 563 joules, minus her initial kinetic, which was 2250 joules. And when we subtract, we get negative 1,690 joules to 3 digits. Is it okay to have negative work done? The answer is yes, because what this indicates to us is that the energy was lost. And that should make sense to us because the energy, the kinetic energy, was lost and used to used to slow her down from 10 meters per second to 5 meters per second. So there's a loss of kinetic energy here, and a loss would be indicated by the negative sign. Number 13. Sean and his bike have a total mass of 45 kilograms. Sean rides his bike 1.8 times 10 to the third meters in 600 seconds at a constant velocity. What is Sean's kinetic energy? Well, we know that in order to calculate Sean's kinetic energy, we have to know his mass and his velocity. What's missing in this problem, of course, is how fast he's going, but they give us enough information to find that out. So we start by calculating Sean's speed. We're told that he travels a distance of 1.80 times 10 to the third meters, and that he does that in 600 seconds. So V equals d over t, and dividing, we get that his constant velocity was 3.00 meters per second. We now can use that to calculate his kinetic energy. Ke equals 1/2 45 kilograms times 3.00 meters per second, remembering to square it, and we should get to 3 digits Sean's kinetic energy of 203 joules. Number 14. In the 1950s, an experimental train that had a mass of 2.5 times 10 to the fourth kilograms was powered across a level track by a jet engine that produced a thrust of 5 times 10 to the fifth newtons for a distance of 509 meters. Find the work done on the train, and if the train starts from rest, find the final speed of the train. I'm going to combine this in all one complete solution here. And this is, again, a work energy problem. W equals delta ET. The only change in mechanical energy here is kinetic because only the train's speed is changing. We write the equation for work, which is F times D. The change in kinetic energy expression would become 1/2 mvf squared, which would be the final kinetic energy expression, minus 1/2 mvi squared, which would be the initial kinetic energy expression. We substitute, we're told our force is 5 times 10 to the fifth. The parallel displacement was 509 meters. 1/2 mass vf squared, and we're told that the train starts from rest, so the initial kinetic energy is altogether 0. Solve for vf, and we should get 143 meters per second. Number 15. How much gravitational potential energy does Tim, with mass of 60 kilograms, gain when he climbs a gymnasium rope of a distance 3.5 meters? This is simply a gravitational potential energy calculation. PEG equals mgh. PEG equals 60 kilograms times 9.81 meters per second squared times 3.5 meters of height gained by Tim. Multiplying those three, and we show a PEG value gained of 2,100 joules to 2 digits without a decimal point is our final answer for 15. Lastly, we have 16. A 10 kilogram test rocket is fired vertically from Cape Canaveral. Its fuel gives it kinetic energy of 1960 joules by the time the rocket engine burns all of the fuel. What additional height will the rocket rise? This is your first exposure to the concept of conservation of mechanical energy, where the initial mechanical energy possessed by a system becomes the mechanical energy possessed by it in its final state. Well, in its initial state, the rocket has all kinetic energy. In its final state, the rocket gains gravitational potential energy and loses kinetic energy. We're told in this question that the initial kinetic energy when the fuel burns out is 1,960 joules. We set that equal to the equation for gravitational potential energy, mgHf. We substitute. The mass is 10 kilograms, g 9.81 meters per second squared. We solve for hf, and we find that to be 20 meters of height gained by the kinetic energy. We'll do 17 and 18 in class tomorrow. If you have any questions, make sure you ask.